Okay, this is Reese's basis. Blah, 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 blah. Um, so if you have this like two basis vector that are not orthonormal, so these are like I and j, and they're really close. And if you want to approximate this like this whatever vector in here in between, this is pretty easy. It's probably about like 0.7 I plus 0.7 like j, and we will get this. It's pretty easy. But if we're trying to approximate here, well, it's probably gonna, well, we can like subtract like this j from this like I, and then we'll go like maybe a little bit here, and then if you do it like 10 times, maybe it'll reach here. So we'll take like 10 times 10 I minus 10 j. Sure. But the thing is, if they're like about the same, like target 1 and target 2, so their like norms are like about the same, but like this coefficient in front of this basis vectors are like completely different. So despite the similar norm of the targets, energy or the coefficients are very different, and it means that the Parseval theorem does not apply, and it only applies in the orthonormal basis vector. So going back, so if he so this x is like the target vector or whatever, or function, and this alpha is like so we've been doing like those, like this, our best approximation is an times like vn, and then like this is like the sum of it n to the whatever big N. So it would be like a1 v1 plus a2 v2 a2 v2 plus da 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 da, right? So that's what this coefficient alpha is. And for example, like this b is the really the limit. So this coefficient can get as small as like whatever, like probably I guess like 0, if it's like 0 vectors, and like the b, if you go like here, like we can see that like this coefficient increases like 10, right? So it could be 10, or so this target 1 could be closer to b, and target 2, this here in between, would be like closer to a. And then there's going to be, you can imagine there's going to be like some limit of how big this coefficient can get, so a and b can get. So that's what they're representing. And we can just rewrite it in this format. So Wn is still the coefficient, and then xt is, the a and vn again, like a1 v1, that thing again, where this is w is a and this is the basis, so the vectors of v, which is like we defined over here as a like Gaussian function curve. So you solve this, you solve it, and then you eventually get this, and where this is still the same, the basis vector v, and then this is the a, so we still have this like an times vn equal x format, our approximation. And then you take the integral of this like 2, right? And that's really you multiply and take an integral. That's you're really seeing the overlap between these two functions, where this black is the coefficient, and this red line is like the basis vector, the Gaussian curve. And then and so we eventually get this thing, and so this whole expression is maximized when w is non-zero only. So it's like it will be just one single line here, only at the frequency that maximizes this thing. And so it would be, this is like not a great accurate. So so instead of here, this is like the maximum, right? And maximum point is this w would be, this coefficient would be just single line that go through. And so this times this maximum would be like, the maximum. Makes sense. And what it meant by maximization is not a best approximation of the target, but what it is more efficient. And so if we go back to the first example, we see the target 2 is more efficiently approximated than the target 1 using like smaller coefficient, right? And so it talks about it. So it's like the maximum in this case, the maximum give us b and the minimum give us a. So which is A and B are really so the minimal and maximum energy the coefficient can have. And what does it mean by efficient is that it's more like that, target 2 than target 1. And why does it matter? So if we are doing digital signal processing, and when we do, like we have to like quantize, it's gonna be like 10, so here's 1010, but it could be like, I don't know, like 100,000, 11,242.444444 or something like that. And so when we're like doing those, like the computer can like drop some like those like little decimal points or like some numbers and round it up. And when you round it up, it's gonna go like from like here, and then when you round like change the, like one of the components, like this A1 becomes like what is this? Becomes like, I don't know, like, so it goes like way over there. And then it's going to be completely different vector, and so we're going to have a lot of error. And so that's why we want to be efficient. And yeah, that's why we want to be efficient.